All right, everyone. Well, this is the last three sections for this unit and in chapter 5. And we're going to start with rational functions. And if you break down that word rational, the root word is ratio. And that's just a fancy math term for us that means fraction. So we're going to be dealing with these functions that have fractions in them. But not just any old fraction. I'm not going to ask you to take 1/2 and add 3/4 or something easy and simple like that. We're going to have polynomials in both the numerator and the denominator. And they can be as simple as a monomial, a one term, or a binomial, two terms. Okay, but it can also be any. And so what we're going to be talking about is what things can we evaluate and what can we not, in order to plug in something to this function. Okay, will we get anything and everything out? And can we even plug in anything and everything? Well, you guys remember hopefully that we do have issues with denominators. We know that we cannot have a denominator be 0. Okay, so that will be what we will talk about, the domain. Remember the domain and range? D comes before R in the alphabet. We're usually dealing with a bunch of X's and Y's. And if you just write these things in alphabetical order, the domain is all the inputs, the X values. The range is all the Y values that come out of it. Okay? So not a whole lot new there. It's just a matter of the look that we're going to be given. Okay? So let me start with this here. Here's a little how-to. If we're given a rational function, how are you going to find the domain? Well, are we really going to be looking for all the things that we could put into this function that will give us something out? No, it's impossible to do, right? There's an infinite amount of numbers just between 0 and 1, let alone just the whole numbers and then the integers on the other side of 0, all the negatives. So what we're going to have to do is really just look for the things that don't work. And the things that don't work are, like we said, when our denominator will equal 0. So that's the first and basically only step in order to find the domain of a rational or fractional function. Okay? Just set the denominator equal to 0, and those will be the things that do not work. Okay? So that's what step 2 says to do, is to find those X values that cause that denominator equal 0. So in reality, you don't need both of these steps. You just need one of them, right? You're going to set it equal to 0 and then find what would give you a 0. And then that would be your domain. Everything, all real numbers except those values. Okay? And you can literally write it like that. All double-legged R stands for real numbers, except tell me what X cannot equal. That's the easiest way. There's two other ways. There's the set builder notation, where you tell me it's the X values such that X cannot be this, right? And then you close it up. Or that looks like a 3, sorry. It's supposed to be a curly brace. And then there's also the interval notation, which is the one that we will most commonly use, where you're going to literally just tell me the interval, the section of numbers that it can be. Okay? But remember, there's a lot of them. So let's say, for example, we said, all right, well, X cannot equal 2. Then we would have to say, it's all the X's except not 2. We'd have to start from left to right on our number line, right? And if we're just looking at 2, and that's our open dot, and it's all of this and all of this less that, reading from left to right, we would have started at negative infinity and gone all the way up to what number? Well, the 2. But remember, the 2 is the one that we said it cannot be, so we got to make sure that we put a parenthesis around it to not include it. If we put a bracket, then it would be included. But then we need to unite everything over on this side as well. And that's where we put the union, right? Like when people get married, they call it a union. Okay? and it would also start at 2, but not including it all the way to infinity. So any of these three options would suffice, but we're going to say that this is the one most often we used. Okay? Set builder notation is what a lot of books will use because it translates more to many higher level courses as well, but this is the easiest. This is the one that we will use the most. Okay? So, what are some characteristics of all rational functions? Well, if it's a rational function, then what do all of them have? What makes it a rational function?
A fraction bar.
Very good, which means it will have a top and a bottom, a numerator and a denominator. And if there is a denominator that has x's in it, then that is going to result in us having what is called, if you guys remember this term, an asymptote. Right? And an asymptote is a line that our graph approaches but never actually touches. Okay? It's more of a guideline for us. And that guideline is going to help us to guide our graph correctly and appropriately. Okay? And the domain of every one of these is dependent on what? What part of that fraction?
The denominator.
Very good. Excellent. And what about the denominator?
Where it equals 0.
Excellent. Great job, guys. Okay, so that's the gist of that section. Of course, we want to talk more about what it could look like. So here's two of the more basic graphs. And I say basic, doesn't get any easier than putting a 1 on top and an x on bottom. You're like, yeah, it would if you put an x on top and a 1 on bottom. But then that's just y equals x, and that's a line. Okay? So obviously you guys can see we have an issue where x is equal to 0. And notice, if I let x be 0, I would get 1 over 0. And we said that that is called undefined. Which means if I put that in for x, what do I get out for my y? Nothing. It's undefined. And so how do we show that graphically? We draw a dashed line, and that is what we call a what?
Asymptote.
Very good. Watch your mouth. No, I'm just kidding. Very good. That is called an asymptote. Okay? And notice our graph approached it on the right side of that asymptote. It went to positive infinity. And on the left side of that asymptote, negative infinity. Okay, we'll talk more about that just like we did with end behavior. Now, doesn't it kind of look like there is a horizontal asymptote as well, not just this vertical one? Doesn't it look like our graph is approaching this as well? And I know it sounds a little funny, that's why we call it a horizontal asymptote, right? Rather than a vertical asymptote. But notice what happens if I squared the bottom. I made it a little bit more difficult. Did we get any more asymptotes? Even though it's squared? No, because if we took the square root of that, then we would get x equals plus or minus 0, and there's no such thing. That's what separates the positives and the negatives. So we still and only have one asymptote there. But notice what it did do was take all the negative x values, which churned out negative y values. Because it's squared down there, notice it took all those y values and made them what? When we square those x values, they will all become y values that are positive because we're squaring them. Okay, now notice it's getting smaller and smaller and smaller. But that's because when we stick in -1 and square it, we get 1, which is 1. We can plot that point. But when we plug in -2 or even +2 and we square that, we get a 4th. So notice my bottom, as the x values get bigger, whether it's to the left or to the right, because it's on bottom, my number is going to get what? My output, my y value.
Smaller.
Very good, Ford. It's going to get smaller. Now, how small is it going to get? What's the smallest it will get?
Infinity.
Ah, close. I like what you're thinking, Kev. If I plugged in 5, we know we'd have 1 over 5 squared, which is 1/25. What if I plugged in 25 and squared it? Well, that'd be 1 over 625. It gets bigger and bigger and bigger on the denominator.
Also, it gets closer to 0.
Ah, very good. And that is exactly what this asymptote is going to tell us. Hey, it's not going to cross this line, but it's going to get really, really, really close to it. Will it ever reach 0? What if I put in 1 over 100 squared? That's really, really small, but is it 0? Will it ever be 0? And remember, that's what we said the asymptote does for us. It tells us what it approaches, but will never actually touch or reach. It's that guideline. Okay? So we are going to call these things arrow notation. Because it never actually equals that number, we're going to say this means what?
Approaches.
Very good. Very good. So that arrow means it's going to approach. Now, this is going to be a little different than what you guys may have remember or ever seen before, and that is you're not used to seeing a little negative on the upper right or a positive on the upper right. You're used to seeing a positive in front or a negative in front, and you know what that means. That means to the right of 0 is positive, to the left of 0 is negative, correct? Well, then we're going to use that same type of notation for these things. But it's going to mean this number, any number, A. But guess what we want to look at? If it's negative, from what side of A?
The left side.
And if it's positive, what side of A?
The right side.
That's right. So if I wanted to talk back about these, and I wanted to say, what is my y value approaching as my x approaches 0 from the right? Or what is my y value approaching as my x value approaches 0 from the left? What would you say for this function? Well, here's 0. What are my y values doing to the right of it?
Increasing.
Forever?
No. Yes?
Yes, that's what that arrow means. That's right. So what number can you tell me that it's approaching if it keeps going up forever?
Infinity.
That's the symbol we made for it. Very good. Now, how about from the left of 0?
Negative infinity.
To the left of it, it's approaching negative infinity. Okay? So that is what we call arrow notation. And this is going to be the very first thing that you learn in calculus. It's called a limit. Okay? That's what it's approaching, but never actually reaches. Okay? So that's what these symbols mean. And you guys know the difference between an x and a y value. All right? We talked about vertical asymptote. Well, guess what? When will we have a vertical asymptote? When our y is approaching positive or negative infinity, just like we saw in these graphs. Positive infinity on both the left and the right. Negative or positive infinity. Still going to have that asymptote. Okay? So if I asked you to find the domain of this function right here, what would you be trying to do?
Find what x is not
Where?
in the denominator.
Only.
Denominator.
Very good. Only in the denominator. So we will set this equal to 0, and those will be the things that x cannot be. Otherwise, we're going to put it's all real numbers except x cannot equal. Can anybody look at this and tell me what they would be easily?
Positive and
3 and
negative.
-3.
Good. All of you couldn't reach to the space bar to unmute yourself fast enough. That's what I want. You should know that that is just the difference of two squares. And you should see that those are going to give me the negative and positive 3. Or you can add the 9 over and take the square root and get that plus or minus 3. Either way you get there, just don't forget to tell me that it's everything but those. Don't just tell me x equals -3 and x equals 3 because you're way off. Okay? Now, one thing I did want to mention, kind of a little segue example here, is what about the top? Does that mean it doesn't matter at all? Because if you notice, if I did factor that bottom and I had this, what do we usually try to do if we can in math?
Reduce.
Yeah, reduce and simplify. Let's make it look simpler. And the only time we can do that is when we're multiplying. Because I know that x plus 3 over x plus 3, anything divided by itself is 1. And I know 1 times that will stay that. So if I can do this, does that mean I should only be listing the positive 3 and getting rid of the negative 3? You see what I'm saying? Does that remove one of our issues of that -3 value that would have given me a 0 in the denominator? Because I can actually take this and put this as my simplified version of that function by factoring the bottom? And the answer is kind of.
Doesn't that mean there's a hole at -3?
Very good, Kevin. Excellent. And that's what's weird. A hole? What are you talking about, man? We're not out in outer space. The black hole. Well, remember, when there were zeros in the denominator, then we knew that those were no y values would come out. And they would approach on either the positive or negative side. But when we have what is called a discontinuity, it's not continuous, whether it's a vertical asymptote or this new thing we're calling a hole, which is just an open dot, you guys. Okay, it's a fancy term for an open dot. Just sounds cooler, doesn't it? This is when you will have what is called a hole. In this case, -3. So it doesn't mean that you're going to have that positive or negative infinity situation. That means you're going to be approaching that number from either side, and there's just going to be an open dot there, and then it will continue. Okay, so I can show you some examples as we progress, but I wanted to mention that. Did it affect our domain? If there's a hole at -3, should we be tossing it out?
No.
No. Very good. Just like a vertical asymptote. The only difference would be at -3, we would have had a little hole right there. An open dot around it, saying, oh, not that value, but everything to the right and the left of it, yes. Not a vertical asymptote there, though, like there was here. Okay? So little nuances, that's just a special thing, and we will call it a removable discontinuity. Because it's not continuous at that value, it's a hole. Okay, but it's something that is not as restrictive as a vertical asymptote. Okay, so little things like that that we have to make sure that we know. Okay, last thing, we mentioned a little bit with those graphs. a horizontal asymptote. And these are much more difficult. But I'm going to make them very simple for you. I'm going to give you 3 little rules, and I'm going to show you just once in one of the 3 ways why it is the way it is. Okay? So bear with me here. A horizontal asymptote is when we go to the far right or the far left, all the way out here or all the way out here to negative infinity or positive infinity. We want to know if our y values are all approaching some number. Okay, like we saw in our graphs up here. We noticed that they were approaching what? Zero. But why? But why is that? Well, remember, if we're plugging in really big numbers, 1, 2, 3, 4, how about 400? Well, then that's going to give me 1 over 400. What if I plugged in infinity, you guys? Can you do that? Can you just take your calculator or your keyboard and just rotate it and put the 8? No, it doesn't make sense, right? The infinity is a little bit wonky. It's weird. It's an idea. It's not an actual number. But it represents the furthest right that we can think of and really, really, really big. So what is this approach? When I stick a 1 and divide it by a really, really, really big number, it approaches 0. And notice for this one, there's a little bit of a gap here to the x-axis, that 0 for my y value. Where this one, not as much of a gap right there, is there? How come this one is a little bit lower than this one is right there?
Because it's squared.
Squared.
Very good. And if I squared 400 instead of just plugged in 400, when I square it, it's going to get bigger faster in that denominator, which means it's going to get to 0 faster. Does that make sense? So let's take a look at some of these other options. Okay. Here's an example, and then I'll circle back to these rules that we're going to have. And there's only 3 options. That's nice, not too bad. Okay, but let's take a look at these rational functions. And I want you to think about plugging in positive and negative infinities. Okay, so if I was to think about this one right here, is there going to be a horizontal asymptote or this other thing that we're going to call a slant asymptote? Slant meaning instead of it being horizontal or vertical, it actually has some slope to it. Notice these are all lines that our graph approaches. But there can be a situation where it goes like this. And you can see that it's still approaching that graph of that line we call an asymptote. Okay? So that's when we have what is called a slant asymptote. And if I was to take this one right here, and I was to think about plugging in infinities, 6x cubed, ooh, that was a bad one, minus 10x over 2x cubed plus 5x squared. Now watch, guys, I'm only going to do this once. I'm not going to do it for every single one of these. And this is preparing you for calculus, okay? Remember I told you one of the most important things in all of math is multiplying by 1. If you guys can multiply by 1, you can do many things in math. Because this is what I have, and I can't change that. But I can multiply by a fancy 1. And the only one I care about is the denominator's highest exponent. Okay? If I want to divide all of this by x cubed, I can do that. It's just like multiplying by 1 over x cubed to each, the top and the bottom. Does everybody see my fancy 1 here? And if that's a 1, then what's 1 times this in pink? Still that, because it's just multiplied by 1, right? So I didn't change it. But by distributing this in to all of this, watch what happens, you guys. This is where it gets a little tricky. Watch. The x cubes will cancel. I get 6. Minus, cancel one of these with one of those. I'll get 10 over x squared. There's my new numerator. Denominator, x cubes cancel out. I get a 2. 2 of these with 2 of those will leave me with just 1. So I just have plus 5 over x. And why did I do that, you guys? If I plugged in infinity here, 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 and here, everywhere there was an x. What's infinity cubed? Times 6, Richard. Don't forget times 6. And then minus 10 times infinity. Divided by, don't forget we got the bottom, infinity cubed times 2 plus 5 times infinity squared. What does that equal? Because that's my y value. I have no idea. Oh, and don't forget, we also got to do negative infinity. We got to do the left side. That's confusing. So I got a little creative and I multiplied by this fancy 1. Because now, if I go to plug in infinity here and here, what did we say any number over a really big number will equal? Anybody? What is 2 divided by, or let me just do 1, because that's what we had up there. We had 1 divided by 10. That's pretty small, isn't it? What if I put a bigger number down there? What did it get?
Smaller.
Smaller and smaller and smaller, the bigger the number got, right? So what if I put 1 over infinity? What number is it going to approach?
0.
That's right. The smallest value that we have, 0. Which means if I plug in an infinity to any one of these, what is this going to approach, this number? What's 10 over a really big number, infinity squared? 0. How about 5 over infinity? What's that going to give me?
0.
And therefore, what are we only left with on top and bottom? Six over 2, which is what?
3.
Silly question here. So
Not silly, not silly. This is a very challenging concept. Go ahead, Rich.
the number isn't actually 0, but it approaches 0, so we notate it as 0.
Bingo. Remember, that is what we called the arrow notation. It's what it's approaching, not what it actually is at that value. And for you to pick that up already, very, very good. That is something very, very important when we get to limits in calculus. Excellent job. Glad you brought that up. Remember, it's what it's approaching, not what it is. And why can it not be that value? What value is infinity? What's the biggest number you guys know?
Infinity.
No, that's not a number. Give me a number.
I don't know, pi?
Pi is 3. You don't
Oh, it's
know a
actually
number
not that
bigger?
big, is it?
It is delicious, but no, it's not a very big number. How about a Google?
Is that 100 zeros?
It's 1 with a million zeros after it. You know what's even bigger than a Google? A Googleplex. It's a 1 with a Google zeros after it. You guys don't believe me? Google it. But my point is, anytime we have things that are approaching infinity or negative infinity in the x direction, and we want to know what happens to the y values, It's very simple. Look at the highest exponent on top and bottom, because what's going to happen to all the others? They're not as big. And when we're talking infinities and negative infinities, they're just going to go to 0. So if you notice this one right here, we can just forget about these and focus on these. And if we did that and we had 6x cubed over 2x cubed and all the rest just became zeros, then what would you guys do with that? You'd cancel the x cubes and say your answer is 3. Now what's 3, guys? What does that represent?
The horizontal answer, whatever the thing.
Very good. Our y value, right, would equal that 3. Our y would approach, like Richard said, 3 as x approached infinity. It would also approach 3 as x approaches negative infinity, because both of these canceled out. So the only thing that would be left are the coefficients, which would give us that y value of 3, because we're plugging in things for x to make them 0 out. Okay? So look at the next one there. Who's winning this battle? Because we're talking infinities. We're talking to the extreme right and the extreme left. Well, here, it was equal, wasn't it? So we had to just drop those and focus on the coefficients, and that was our answer. Where this one, who's going to win the battle? The top or the bottom?
Top.
And if the top wins, then we know if we just took all this and it went, oop, too much there. That stuff went to 0, then I would be left with an x squared over an x, which if we canceled, we'd get x. So this time, we know y would approach what as x approaches infinity or negative infinity?
The same?
What?
Same as x?
Very good.
Would it be approaching the x-axis? Is that what it means?
No, just like here when we plugged in the infinities, it made these get really, really small. We said so small that it's going to be like nothing. And so we were only left with this, which was our answer. Where this one, if we did that same thing, and again, I could do all of this with you again, but for time's sake, we're already going long, right? We know when we plugged in our infinity for x here, our y is going to come out infinity. And when we went to the far left, we knew our y would be what? Negative infinity. We're still evaluating those numbers, but like I corrected Richard, when he tried to give me the biggest number he knew, infinity is not a number. It's an idea of a really big number to the right or to the left. Or up for positive, down for negative infinity. Okay, very good. Let's look at the last one then. X squared versus x cubed. Who's going to win that war? And again, remember, I'm not looking at anything else other than the highest exponents of each. Who's going to win that war?
Denominator.
Good. So now if I have x squared over x cubed and I canceled 2 of these with 2 of those, I get 1 over x. And so if I look back at this same problem here, right, that's what all of them are going to look like. When I put in an infinity there, what is my y value going to approach?
0.
0. Very good, right? Remember, 1 over a really big number is going to be the smallest thing that you can think of. How about negative infinity? What if I put a negative infinity in there?
Still 0, right?
Yeah, very good. It just is going to approach it from which side of 0?
The left.
Left side.
Very good. Excellent, guys. Does that make sense? Should I put -0? No such thing. It's still 0. It just would be coming from the left side rather than the right side. Awesome. You guys are doing really well with this. This is calculus level content. Okay. So let's put it all together and see if we can graph. If we were to sketch this graph, well, I'd want to know a lot of things, as many things as we've talked about so far. And what do you think I would start by doing? And again, they give you an 8-step process. You don't need all that, but if you want to take a screenshot of that or a picture with your phone, that's fine. Otherwise, I'll post this and you can look back on it. But where do you think we would start with this? Where did we start today with?
Find the zeros of the denominator.
Very good. And what did those represent?
Vertical
Asymptotes.
Awesome. Very good. That's the very first thing I always like to do. Let's start with that. What it can't be. Those guidelines we call vertical asymptotes. And can you look at that and tell me what two things would not work?
2 and -2.
Very good. How'd you get that so fast?
Difference of squares.
Awesome. Now remember, the reason we dash these lines is they're not part of my graph, but they're necessary. Now, what do you think would be our second step? If we set the bottom equal to 0, do you think it would be good to know what the top equaling 0 would be? Well, remember, if we factored the top and the bottom, like we talked about doing in the last example, we knew that this was going to be x plus and x minus 2. What would the top be?
Three and 2.
And what would be what? Positive or negative?
Negative 3,
+2.
Positive 2 and -3 to give us that -1 in the middle. Very good. Excellent. But notice, Richard, we just talked about finding those vertical asymptotes. We drew them out, but remember we also mentioned we could remove one because of this. So anytime before you start and you see that you have polynomials, especially these quadratics, try to factor them. Because you can see here, we actually have what is called a removable discontinuity, which means instead of just having vertical asymptotes at x equals -2 and +2, there will only be one where x is equal to 2 everywhere. Y can be whatever. Which means I'm going to have to remove this one and make it a what instead?
A hole.
A hole. Now, where do I make that hole? Is it always just right on the x-axis? Or do I put it up here or down here? Where do I put it? Well, I canceled it out. Let's plug it in and see. Let's plug in that -2. Let's plug in -2 here and -2 there. What would that give me on top?
-5.
-5 and what on bottom?
-4.
-4 for a simplified version of
5/4.
5/4. Well, then I know if this did not exist there in the simplified form of this function that they originally gave us, if I was able to plug in -2, this is what I would get out for my y value. But what did we just find? We can't have anything there. So I'm going to go to 1 1/4, and I'm going to put a hole at -2. Everybody good there? Okay. Do me a favor. Put down your pen or pencil just for a second. Thank you, Emily. Gently, though, because that's an Apple Pencil. That's expensive. And I want you to look at this and tell me, what is the horizontal asymptote? Don't say it out loud yet. Everyone just think to yourselves. Look at this and tell me what the horizontal asymptote would be. Can you all see it? With the horizontal asymptotes, remember, we're talking all the way in the extremes, which is positive and negative infinity for x. And we want to know what our y values approach, if anything. Sometimes it's that slant asymptote like we talked about. And can you see what's going to happen? Take the highest and lowest and compare them. Who's going to win this war? Nobody. It's a draw. The x squareds and x squareds are going to cancel out. And therefore, what are we left with?
1/1.
Very good. They're coefficients. Which means we just found the y value equals or approaches what? When our x values approach positive or negative infinity. So guys, there's one thing you need to know about horizontal asymptotes. They only apply to the extremes. They do not apply to our little graph right here. This little window of the graph that we're making. We're talking all the way out there. So please, please, please do not put your horizontal asymptote all the way through the graph. Because guess what? You can cross through this, whatever it looks like. Okay? You'll never cross through here. That's what that's saying. But the horizontal asymptote we just found were what? That means way out here and way out here. Are you guys starting to see a little bit of my graph developing? A little bit. We just got a bunch of guidelines and one point that we know it approaches but doesn't ever actually reach. So we need some actual points. And so from this juncture, what we want to do is try to find some intercepts. The x and the y intercepts. Do you guys remember how to do that? In order to find intercepts, we let the other letter equal 0. Remember that? So if you want to find an x-intercept, you're going to find the x, then let y be 0. However many there might be. To find y-intercept, usually there's only one. Okay? Then we're going to let the x be 0 and find our y. Okay? And once you do all of this, then you'll be able to graph very easily, just figuring out whether it's going to be up here on the right or the left or down here on the right or the left. And how can we find that easily? Go to the simplified version. You don't even need to use those because they're going to give you the same thing anyways, right? Just look. Am I going to be to the upper or lower part of this line to the right? Well, remember this is 2. Give me something to the right of it.
3.
Okay, I don't like 3 because 3 gives me a 0. So you got to be careful with your choices. Just think of something just to the right of 2. If you took a little bit more than 2 and subtracted 3, what would it be?
Positive.
Negative.
If you took a little bit more than 2 and subtracted 3, it would be negative. Very good. What if you took a little bit more than 2 and subtracted 2? That would be positive. And therefore, what does that come out?
Negative.
And that means I know I'm going to be that and not this. Can we do the same thing to the left of 2 to figure out this or that? Yeah. Can we set the top and the bottom equal to 0 like we already have done to figure out whether it crosses through the x or the y axis? Put all those pieces together, you end up drawing a nice, smooth, continuous graph that goes like this. And we're done. Okay? A lot going on there. For time's sake, I'm going to skip the rest of this. If you ever want to check your answers, what can you always do? Go to Desmos, GeoGebra, your graphing calculator, anything, punch that same function in, and once you graph this, you can then compare what you came up with. Okay? Remember, it's called a sketch. Doesn't have to be exact. But you all should know that we're doing something like this down here. Every once in a while, it could come up and then back down, but usually not. Okay? So these are the types of things that we want to add on to find where it crosses through the X or Y axis, for example. And then that will give us a better reading of where to graph this, for example. Okay? So I want to try to run through these last. That was the longest one for sure. And I apologize for the time of the group quiz and things like that. May have to rethink these moving forward if you guys want me to do these lectures, because there's no quick way to explain all the stuff that I just went through with you. Some of you guys are probably still thinking it was too fast. Okay? But the next two sections aren't nearly as long. Okay? 5-7, we're going to talk about the inverse, which remember is just a fancy term for reverse, and then root or radical functions. So inverses is just another way for us to say that one undoes the other. Adding, subtracting, multiplying, dividing, squaring, square rooting. So if I say that G and F are inverses of each other, and you plugged something into F, and you got that value, and then you plug that into G, well then you should get the X back out, because these are going to undo one another. And it shouldn't matter if you did G of F or F of G. If they're inverses, whatever you put in, these will undo each other. You should get that out. Okay? Remember, these were called compositions of functions. When we did F of G of X, we had one function that was composed of another. Right? So it's really simple. I only like it to put 2 steps. All you do is, if you want to do the inverse, you do the reverse. You switch the X and the Y, and then solve for the quote-unquote new Y. That's it. Now, if they give it to you in the function form, then they're going to give you that extra step and say, you know what? What's easier than putting F of X? Is just a Y value. Okay? Otherwise, we have switching of the X and the Y, solve for the new Y. And this is the symbol we give for inverse. It's that little -1 exponent. Okay? Now, in order for some of these things to be a function, we have to what is called restrict their domain. So if you guys remember when we were graphing parabolas, we knew that parabolas were a function because of the vertical line test. Remember that? For every x, there's 1y, 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 1y for every one of these x values. But what if I had this and I wanted to do the inverse, the reverse? Well, instead of the vertical line test, guess what we're going to use? Horizontal line test. We will do this to test. And if you can notice, fail, fail, fail. There's only one point on this entire thing that would not fail, and that's at the vertex. So how can we make a parabola, for example, be, when we do the inverse and we reverse it, a function? We take half of it. Because now will it pass? Yes, yes, yes. So we'll say, all right, we got some function like a parabola, but in order to find the inverse of it and find it, we're going to say let x only be greater than or equal to 0. So that when we graph this thing, we will only be looking at this half of it and not this half. That way it too, its inverse, that is, will also be a function. Okay? So it's not that big of a deal. It doesn't come in that much. It doesn't come up that much, I should say, but it is something that we want to make sure that we can do and realize why it's done. So here's a couple of quick examples. If you guys want to do one or skip them and let you guys do more on the group quiz, you guys let me know. Or I can do one or both. It's totally up to you guys.
For the first one, do we just cube it? Or I mean, yeah, square it.
Yeah, so remember, first step, make it a y. Second step,
Oh.
switch your x and your y. So now it's going to be x equals what?
Got it. So x equals y.
Cube root of y plus 4, excuse me.
Got it.
But remember, we always like it to be f of x or y equals.
Mhm.
So when we did that first step by switching the x and the y places, now we want to solve for that new y.
Okay.
So very good, Ricky. What are we going to do first?
So like I said, just yes. Can we just square it just to get rid of the square root?
It is not a square root, but you're right. We are going to cube it to get rid of the cube root. Very good. So these will cancel out, and I will have y plus 4 on one side and x cubed on the other.
Mhm.
And what's my last step to getting y by itself, everyone?
Just add 4 to the other, or yeah, subtract 4 to the other side.
Very good. Subtract 4 to both sides so that that cancels, and I get y equals x cubed minus 4. It's that simple. Here's the only issue. At the beginning, they told us f of x or y is equal to this. Now you're telling me y is equal to that. Well, which one is it? We need to know which one is my original function and which one is the new inverse function. And so all we have to do, since they gave it to us as f of x, we got to replace back with the f of x. Some more room here. And we have to tell them that it's the inverse. And in order to do that, we will put this -1. And we put it after the f to let you know it's the inverse function, not x to the -1, which is equal to 1 over x. Okay, so just be careful because we do have previous knowledge with that -1 exponent. Okay, so the only reason I listed 2 is because it gets a little bit harder when there's 2 x's. Because now when we do the switch with the x and the y, now we're going to have 2 y's. So if you guys want me to run through this one real quick as well, I can. Anybody want me to? Otherwise, we can move on. We're all good? Do you want me to do it? The 3 faces I can see aren't making a face, so I will move on. Okay? So notice they gave us a squared function we call a quadratic, which means it's a what graph? Parabola. Very good. And if it is a parabola, remember this is going to be a shift of what?
3 to the
Negative
left.
3.
Very good. Left 3, which is why they put a restriction. They're only going to give us half of that parabola, which would be over here. Very good. So I can graph this original function. 1, 2, 3 to the left. There's my vertex. If I square it, I go over 1, up 1. Over 2, up 1, 2, 3, 4. And this would be the shape of my graph. Now notice I'm only doing things greater than or equal to -3. I'm not doing the other half of it because then that inverse would not be a function. This is still a function. This is still a function. But they got rid of this half so that the inverse would be a function. Now guys, this is something really, really cool about inverses and their functions when we graph. What is the inverse of y equals x?
X equals Y.
Did you say anything different? Brianna, it was just the order that you said it in, right? So the one cool thing about this function in particular is that you get the same thing out when you find the inverse. And we should know the graph of this. Is that. That's my y equals x line. And guess what that represents? That's my mirror. Because if I was to take every one of these values that I graphed and I switched them, which you guys already know, this is the point -3, 0. What's the inverse of that then?
Zero, -3.
Good. Do you see if I looked at the mirror here, it's just right over there? My graph isn't completely drawn to scale, right? Those ones are a little bit closer. But do you see how the mirror is there? Same distance on the other side? What's this value? -2 tick marks and then up 1. What's the inverse of that?
1, -2.
1, -2. Can you see how it's a mirror? Here to here, same distance. Here to here, same distance. And then the last one that I graphed was here, which was -1 what?
4.
Good. What's the inverse of that?
4, -1.
And if I graph this, can you see my beautiful butterfly?
So it's just basically flipped.
Yes, very good. It's about that mirror. It's going to be the same thing on both sides. Now, don't forget, what if I asked you to actually find it? Well, then I would rewrite this as x and y in reverse equals, and I could even say that this would be y is greater than or equal to -3 now. I could switch all the x's and all the y's. And can you guys see that on my graph? Now y's are greater than -3. Right? All of this plays true. Now don't forget, you need to know how to solve. So this time we would take the square root to get rid of that. And now I'd have y plus 3 equals the square root of x. And what's my last step?
Subtract 3.
Subtract 3 to both sides. And does that 3 go underneath the root?
No.
No, it is the square root of x and then -3. Very good. And instead of this, I'm going to say it's my inverse function. And do you guys remember from a few weeks ago what the square root of x looked like? That was that 0, 0, 1, 1, 4, 2. Remember that? All the square roots that we knew for the x. 0 we knew, 1 we knew, 4 we knew was 2. And then we graphed it. Notice it looks a lot like this, just shifted what?
Down 3.
Yep. See how it's all coming in? Okay. So that's it for that section. The last one we've already really talked about are polynomials and rational inequalities. And if you guys wanted to, I'd be willing to do this on Wednesdays and then do our group quizzes on Fridays if you guys would rather. Okay, we could talk about changing that up and doing that because I'm just trying to explain these as best as I can and as quick as I can. But I mean, we're already at like 5 after 12, and that's not going to give you guys a lot of time to work on your group quizzes. So I can have them open on Wednesday and then have them close on Friday if you guys would rather, so that anybody that wants to actually come and work on them in a small group, we can do that on Fridays. But let's keep that line of communication open, okay? You guys let me know. I'm open to adapting. All I want is for you guys to learn this material, okay? So last section, you guys okay, or do we need a break? Keep going, I hear. Okay. Polynomial and rational inequalities are just that. We're going to be dealing with polynomials and fractions, but now instead of them always being equal, they're going to be not equal, inequalities. So we're going to solve them the same way that we always do. And look, guys, here's the notes. There's not much to these that are new. It just adds a couple of extra steps at the end. Okay, so I'm going to just do a few examples, and that's it for this. Okay, so if I ask you to solve this equation, just pretend this wasn't there and it was equals. What would we all try to do first? Let me rephrase that. What should we all try to do first?
Add the 8.
Factor.
Oh, no, factor.
Yeah, very good. Don't just add the 8. We like it when it's set equal to 0. Right? Factor. That's our quickest, easiest method. If we can't factor, then we had two others. The completing the square and the quadratic formula. And you remember a week ago, we learned if it's not quadratic, then we have the plus or minus P over Q stuff, which is our last ditch effort. We don't like that. I got some hate mail from that one, right, Richard? Isn't there a better way? Unfortunately not, okay? So hopefully we can factor because that is our quickest, easiest method. That's why we learned it first, okay? X and X, if I was to FOIL, is the only way I'm gonna get X squared. I know what comes to mind immediately of 8, a 2, and a 4. And I know that those also have to be a positive and negative to make negative 8, which also is going to give me a difference of 2. Perfect. All I got to figure out is which one is positive and which one is negative. And because I knew they were different, I looked to the middle sign to see which one goes with the bigger number. And because it's plus, positive 4, negative 2, to give me that positive 2 in the middle. Great. I was able to factor, which means guess what I just found?
The zeros?
Ah, very good. I was waiting to see if somebody would say it correctly. Awesome. The zeros, which means set this and this factor equal to 0. We found X is equal to positive 2 and negative 4. So what? Who cares? Because they don't. They didn't ask us where it's equal to 0, did they? They asked where it was what? Less than 0.
Greater, oh, less.
Yeah, read it from left to right. Less than 0. But that's why we first found where it was equal to 0, because if we want to tell them where it's less than 0, we need to know where it is 0 first. So the cool thing is, you guys, just pretend this is an equal sign, attack it the same way we always have. But what I'm going to do is I'm going to draw a number line, and I'm going to label those two critical points of, now careful, don't just put 2 on the left because that's where you found it, and then the negative 4 on the right. No, guys, this is a number line. Okay, so I'm going to put the negative 4 here and the positive 2 there. And are these solutions included in this?
No.
Are those solutions to this?
No.
No, very good. If it was equal to as well, then yes, this would be a solution and this would be a solution. But that means everywhere else is either going to be, since this is the only two places that it is 0, we're going to put a big open dot there and there because we know that those are not solutions. But that is where it is equal to 0. And what we wanted to know is where it was less than 0, meaning we want the negative values. So all we have to do is figure out if this is where our graph would be 0, then we need to know if it's above or below. Above or below in every other area. All 3 what we like to call intervals of my graph. And guess what? If you give me an X, I can tell you the Y value very easily by just plugging it in. And guess what? I don't want to plug it into this. I want to plug it into these because it's way easier. So check this out, guys. I'm going to just do this so that I can see that I have 3 different intervals, and all I'm trying to figure out is if it's positive or negative. Which means pick something to the right of 2.
5.
3.
God, I knew somebody was going to choose 3. Brianna went above and beyond and went with 5. Hey, guys, how about 100? Because that's what we're trying to keep it in here. There's your emoji. Right? Is 100 to the right over here? Yeah. So why choose 3 or 5 when all I care is if it's positive or negative? So plug in something that's simple and figure out what it is. Is it positive or negative? So plug in 100 here. Subtract 2. What do you get?
98.
Don't say 98. I don't care. Right? What is the only thing I care about?
That it's positive.
Positive or negative.
Yeah, very good. So yeah, I could figure out exactly when I plug in 3 or 5 or whatever my y value is, but I don't care because I'm not graphing this. So when I plug in, for example, 100 here, I know it comes out positive. What happens when I plug in 100 here? Add 4, it's still positive. Now, how about, I think it was Anthony that said 3. Plug in 3 here and here. Does it make you think a little bit more? Maybe. Sometimes. Depends on the problem. So that's my point. Make it simple. Just pick something way out here and see if it's positive or negative. And if we multiply those, then we know everything to the right of 2 is going to be positive. Now pick something between -4 and 2. What's something really nice?
0.
Beautiful. Now I would actually plug 0 into this. Or the factored form, doesn't matter. But I like this one better because what happens to these when I plug in 0?
They become 0.
And I'm still left with the what though?
A negative.
So I know it's going to be negative. Now if you plug in 0 here and I subtract 2, I get a what? Negative. Plug in a 0 here and add 4, what do I get? A positive. Which means a negative times positive gives me negative. Either way. Okay? And then what am I going to choose for way out here? To the left of -4?
-100.
Beautiful. It doesn't have to be. You can do -5 or something. But a lot of people pick -3 because they're thinking they don't know their negatives very well yet. Okay? So I just like to play it safe. Plug in 100, plug in -100, and then anything in between that works well, like a 0 or 1, things that are nice. Okay? So good. -100 into this is definitely going to be what?
Negative.
And what's -100 when I add 4?
Negative.
Without thought, right? If I had -5, I might have to think a little bit harder, just a little bit. Still shouldn't be difficult. And what is a negative times a negative?
Positive.
Now, guys, I'm going to give you guys a shortcut, but only for those of you that are paying attention and really understand this. Do you remember the multiplicities we talked about the last 2 weeks? And do you remember when a multiplicity was to a 1? What did we know it was going to do?
Cross.
From a positive to a negative to a positive. And do you guys see the shape that it ends up making?
Parabola.
Hey! Isn't it cool how it kind of all plays in and you're finally getting to see?
It's all coming together.
Some of you guys are like, they've been trying to trick me this whole time. You're like, why didn't anybody really put this all together? Don't worry, I'm here now. Okay? That's why I'm the world's greatest boss. You guys see my office? No, again, I'm just trying to get you guys to see all those connections. Okay? And some of you still won't, but hopefully you can. Which means all you really had to check was that positive 100. And once you found that this was positive, then guess what? I'm not doing any of this. I'm going opposite, opposite. It's going to change. And I'm done. All I got to do is give them their answers that they wanted. And when they ask me to solve An inequality, I don't just have the one or two answers anymore. I have a whole bunch of them. And what kind of answers did they want? The ones that were less than 0. And didn't we find where the things would be less than 0 down here? So then all I'm going to do is cross this and this interval, and I'm going to read all we do for the x's is left to right. And when do I start hitting my solutions? Not until I get to what number?
-4.
-4. Is -4 included as a solution? No. Very good, which means what should I put?
Open in parentheses.
That's right. Comma, then all of these work all the way until I get up to what? 2.
2.
And is 2 included? No. But guess what? Letter answer A on your multiple choice test might say. And without looking, you're like, oh yeah, sweet, that's what I got. And then guess what? You did all that work for nothing. Well, maybe I'll give you half a point. Depends on my mood. No, I'm just kidding. Be careful, that's my point. Pay attention to those details, okay? If they had an equal sign underneath there, guess what? Now this is my answer. Because these would be where it's equal to 0, and this would be where it's less than 0. And just so we don't have to do another example of this type, what would happen if I switched it to greater than or equal to? Now what kind of answers would we be looking for? The positive cases. And how would we read those from left to right? When have I started hitting my solutions? All the way out here, which starts with what number?
-infinity.
Very good. And remember, we'd never include those because they're not actual numbers. And it would go comma all the way up to what? For the positives.
Till -4.
And let's say it was equal to this time.
Could be a bracket.
Very good. But those aren't the only positives. There's also positives over here. So we need to unite it with the other interval or section, which starts at what number?
2.
And if it was equal to, then we would include these points, right? So I'd throw a bracket around my 2 and go all the way to what?
Infinity.
And beyond. That's right, Brianna. Very good, Buzz. Okay? So you can see the drastic difference between the two answers just by me switching this symbol. So what's my point? Pay attention to details. Okay? These little brackets versus the parentheses matter. Knowing that greater than or less than means positive versus negative. The equal to, including those values, all of that matters. So that when we get to the rational inequalities, we virtually do the same thing. Okay? So last one here, and then we're done. Okay? I won't even make you guys stay for the group quiz if you don't want. It was a long one today. I apologize. Again, they'll give you a bunch of steps. Don't worry about that. I'm more concerned that you know I got to get this equal to 0. And I picked a hard one just to do with you guys so that hopefully you can do the easier ones. A lot of times they'll just have even it factored for you in something like this. Okay? Then you will just set the top and the bottom equal to 0. And will we ever include the bottom, Richard?
Yeah, why wouldn't we?
Because remember, we just worked on our domain in the last section. And we said that those were the things
Oh,
that would
sorry. Yes.
That's okay. It's been a long one. Just trying to include it because you were talking about the domain earlier, right?
Yeah.
Can we include the top ones, though? Now, notice I said, can we? Should we always? Depends on if it's included or not. If it's equal to 0, then yes. If it's not, then we will have those open dots like we did here. Okay, so by giving you this first problem here, again, I gave you a very difficult one, a challenging one at the beginning, just so that I could go over a more laborsome problem than the easier ones. I know I'm going to have to subtract this 1 over x to both sides. Got to get it equal to 0. So now I have 1/2 minus 1 over x minus the 3 over 2x squared, all greater than or equal to, everything canceled out. Now I got the 0 that I wanted. Everybody good with that first step? Okay. Then obviously I don't like that there's 3 different terms. I want to get one rational function. I want one big fraction, which means, unfortunately, what do I have to get in order to add or subtract fractions?
Common denominators.
Common denominator. That's right, Brianna. So that means here comes that fancy 1 again. And obviously this has a 2 and an x squared. This has a 2 and an x. We can get there. I can get everything to be 2x squared by multiplying by x squared over x squared on this one and a 2x over 2x to this one. So that then gives me an x squared over 2x squared. Please don't cancel the x squareds. If you cancel those x squareds, guess what? You're right back to where you started. Okay, remember why you're doing what you're doing. Don't just do things to do them. Don't listen to Nike. 2x over 2x squared, and then minus a 3 over 2x squared. Remember, this was all greater than or equal to 0. Now what? Well, I worked really hard to get my common denominators. I have this many of these, this many of these, and this many of these. So I have a certain number of these. X squared minus 2x minus 3 of them, to be exact. And now hopefully you see that we have that one rational or fractional equation, which, by the way, guys, some of them will just have you start here. Okay, some of them will already have them factored and just have this. Okay, but for us, we know that we want to take that a step further and factor. Let's factor the top. The bottom, there's nothing really to do because it's just 2x squared. And x, obviously 1 and 3 are our only options to get a negative 3, but I want to get a negative 2. So the negative is going to go here, positive 1 there. All good? So help me out, gang. Where are my zeros?
One and 3. Oh, sorry, -1 and 3.
Good, good catch. Are those the only zeros, Ricky?
2x squared also equals 0.
Yeah, very good. We have to set the top and the bottom equal to 0 to find all of the critical values where it might change from one to the other, or those vertical asymptotes, which is what the bottom will be. Okay, so very good. We have the top, and do they want to know where it's equal to 0? So we're going to say at -1 and 3, and where can x not be a 0? What if we set this whole thing equal to 0?
√2.
Actually just be a 0. Right? Divide by 2, that gets rid of the 2, and then take the square root of 0, you get 0. Technically it'd be plus and minus, but no such thing. So we get, now that is something that's important. I'll get back to that in a minute. This is something that's going to be a what? Just say it now.
Parabola.
A multiplicity. Which when we go to graph it on our number line, we know it will be the same around that value. Where if they're all multiplicities of 1s, we said it would be the opposite from one to the next. Okay, So what are we going to do with all of these zeros? We're going to go graph them. Now, I'm not even going to do the X and the Y axis, which I could, but I'm literally just going to take those 1, 2, 3 values. I'm not even going to space them out evenly. I don't really care about that. I just care about those values. But I do have to write them from smallest to biggest. So what's going to be the left one there?
-1.
And then what?
0.
And then our last one, 3. Very good. Now remember, which ones are we never, ever going to include, Richard?
0.
Good. Our denominators, which happens to be 0 this time. Okay? Never include the denominators. So we will always put a big open dot there. Can we, and for this one, should we include the numerators as solutions? Yes, very good, Brianna, and everyone else. Why?
Because it's
It's
greater than or
great,
equal to.
They said equal to 0, and the top is where it would actually equal 0. We know 0 divided by any number is 0. So very good. We will include these, which means I'm going to put a closed dot at -1 and at 3. And then what I like to do, just to cut it up so that you can see, with 3 points, it actually splits it into 4 sections or intervals. And do I literally have to test all of them for the top and the bottom to see if it's positive or negative for every single one of these? Some of you may have to, but not Ricky. He said, no, I don't have to, because I know about multiplicities. I learned the previous 2 weeks worth of stuff, and I know how it translates over this. Now, if you wanted to, let me just do it for the first to show you. I'm going to use the factored form. Now, guys, check out how I wrote the bottom already. Why do I not even have to test the bottom? It doesn't matter what I put in. I'm going to square it and then multiply it by 2. And no matter what you put in, positive or negative, big or small, when you square it, what does it come out? Positive. And when I multiply it by 2, it's going to stay positive. So I don't even have to test the bottom. Only things I have to test are these two, which instead of using the original form, I'm going to use the factored form. Much easier. So plug in something like
500.
Ooh, he's going big time. 5 times as me. Sure, Ricky, it doesn't matter. That's my point. Just something that makes it easy. And you know, when you plug in really big numbers, what are they usually going to come out when you're adding or subtracting?
If it's positive or negative.
And it's going to come out positive because really big numbers, right? Good. So 100 plus 1, positive. 100 minus 3, positive. Which means what is everything to the right of 3?
Positive.
So from there, should I just go negative, positive, negative, just alternate all the way through?
No.
Why? Why not? Why can I not do that for this particular one?
It's a multiplicity of 2.
Which means around the 0. Around the 3, we know it is going to change, isn't it? So we know since that's an odd, it's going to go to the opposite. But around the 0, since it's a multiplicity that's even, we know even means it's going to what?
Just,
Stay the same.
yeah.
And then around the -1, which was a multiplicity of odd, a 1, then I know it's going to go to the opposite. Do you guys see how much time that can save you if you understand the multiplicity stuff? Because if not, guess what I'd have to do for every single one of these? I'd have to test them, right? And plug in something between -1 and 0. Ugh.
Point negative.
Yeah. -1/2. Now, remember, the good thing is we don't care what it comes out. We just care if it's positive or negative. So plug in -1/2 here and add 1. What are you going to get? See, some of you guys are like, calculator time. No, you should know -1/2 plus 1 is positive. How about negative anything minus 3 more, what is that going to be?
Negative.
Negative subtracting more is going to be even more negative. So that's negative. And if you didn't believe me when I was doing the alternating thing and then stayed the same around the multiplicity, I wanted to confirm that it does come out negative here. Okay, so that's the main difference between the polynomial versus these, what are called rational. You have to take the top and the bottom and set it equal to 0. And which one will we never include?
The
The
denominator.
denominator. And which one can we include? The numerator, but only when it has the equal to included. Okay, now don't forget, what do we have to do with this in order to finish? What did they want? What kind of answers?
Interval notation.
Any that are greater than or equal to 0, which means we only want the what?
Positives.
Positive things, that's right. And how do we read? We read left to right. So what am I going to be starting at?
Negative infinity.
Negative infinity, never including infinity, so always the parenthesis, comma, all the way up to what for the positives?
-1.
Now, is that -1 going to be included with a nice big hug, that bracket, or is it going to be
Yes.
excluded with that kind of weird hug that you give people you don't really know?
The bracket.
Yep, this one is included. Okay, then we're going to have to jump all the way over to what?
3.
All the way over. We don't want any of the negative stuff.
No.
All the way over to 3.
And positive infinity.
Which is included all the way to positive infinity. And that will be our final answer. And again, pay attention to those details. And if you guys don't know yet how to input infinities into the My Open Math on Canvas, it's 0, 0. Okay, that's how they do the infinity symbol on there. They just put 0, 0 to make it look similar. All right, my friends, that is it for today. Wanted to make sure that I went through all of this in detail.